Thank you very much. Good morning, everybody. Let's continue our discussion from last time. We started looking at the wavelength routed networks and the concept of how do we assign the routes and how we assign the wavelengths. We started by defining what is known, let's review it quickly, the light path, the concept of a light path. A light path is an all, we call it a light path, is an all optical communication channel. When we say an all optical means what? No requirement for optical electrical optical conversion. And we said the following: if two nodes can communicate via a light path, we regard this as a single hub. A single hub, even if the nodes are not attached directly via what? A single fiber. What that means is the following. Let's look at a couple of examples so that you understand what I'm talking about. I will let you write this in a minute. Let me just show you. If you see this node, for example, and this node, they are not connected directly. These two nodes are not connected directly. If I can establish a light path, which is a what? Which is an all optical light path, continuity. There's a constraint that the lambda, the specific lambda, has to be available on this one and this one. If I establish a light path in here, then this one and this one are regarded to be connected by a single hub. We call it a what? A single hub light path. A single hub. Even though, how many hubs are there physically? Physically, how many hubs? There are two hubs. I want you to distinguish between what? Distinguish between what is known as a physical topology and a virtual topology. A physical topology and a virtual topology. A virtual topology is a set of what? Set of nodes connected by what? By light paths. Set of nodes connected by a light path. Let's see if you can help me with a couple of examples to understand it before we get to the problem of the wavelength assignment. Let's assume, for example, consider the following. Star topology. Star topology. This is the physical one. This is the physical topology. Let's assume that we do have these nodes S0, for example, S1, S2, S3. Just an example. This is S3. And they are connected all via a what? A passive coupler. This is a passive star coupler. Now, keep in mind, a passive star coupler, what is he going to do? He is going to combine all the wavelengths, incoming wavelengths, and then what? and then he will split them to all what? To all the nodes. Clear? Now, assume each node can transmit at a certain wavelength and receive on another. What does this mean? Let's take an example. Let's assume this one can transmit at lambda 0, this one can transmit at lambda 1, this one can transmit at lambda 2, this one can transmit at what? Lambda 3. Just an example, and let's look at the reception. Suppose this one can receive at lambda 0, this one can receive at lambda 1. This is just an example. This one can receive as lambda 2, and this one can receive at lambda 3. Let's understand one more time, what does this mean? This is the physical topology. Clear? This is the physical topology. Let's understand first of all, what does this mean? We have the 4 nodes, each sending at what? Is sending at a different wavelength. By the way, can they transmit at the same wavelength? Can they transmit at the same wavelength? In other words, can this one send at lambda 0 and this one send at lambda 0? No, they cannot. Why? Because there will be a what? There will be a collision. Remember, the passive star coupler, he will combine all the wavelengths and then what? Split them to all the outgoing ports. Clear? Okay, so in this case here, this one is transmitting at lambda 1. He can only, what is the coupler is doing? When he get all of these lambda 0, lambda 1, lambda 3, lambda 2, he will combine them, and what will he send? He will send to all of them lambda 0 plus lambda 1 plus lambda 2 plus what? Lambda 3. However, this one is only able to receive at what? Lambda 3, which means the optical receiver here is tuned to only a single wavelength, which is what? Lambda 3. Did you get this or not? Which means what? The lambda 0, the lambda 1, the lambda 2 will not be what? Will not be received. Only the lambda 3 will be received. What is the virtual topology? Can you show me what is the virtual topology? This is the what? This is the physical topology. The virtual topology is like this. This is S0, S1, S2, S3, and this is the virtual topology. Lambda 0, lambda 1, lambda 2, lambda 3. The virtual topology. Again, the virtual topology is a unidirectional link. Did you get it? I'm not sure. I'm not sure that you get it. In other words, this is the physical topology, is a star topology. But in reality, the way it is working, it is working as a what? As a ring topology. What does this mean? What does it mean? S0 can only send to who? S1. A single hop can only send to what? S1. Why? Because S0, there is a path. Is there a light path between S0 and S1? Is there a light path? There is a light path, which is what? Lambda 0. Did you get this or not? So this is equivalent to a what? A virtual topology. S0 is connected to S1 by a what? By a lambda 0. Did you get this or not? Yes? Okay. How about this one and this one? Is there a light path? Between this one and this one, is there a light path? What is the light path? Lambda 1, lambda 1. That's a light path. So it means, by the way, is this connected to this? Physically. Is this one connected to this? No, it's not connected to this. This one is physically connected to the what? To the pass coupler. Are you following me on that? By the way, in reality, how many hops is this one going to go? It's going, first of all, to go to the passive coupler, and then what? To the S2. Did you get this or not? But in the virtual topology, are they connected by a single hop? The S1 and S2, are they connected by a single hop? They are connected by a single hop. That hop is what? Is a lambda 1. It's a light path. There is a light path between S1 and S2. It's a lambda 1. Clear? Similarly, between what? S2 and S3, and between what? S3 and what? S0. Clear? Clear? In this case, by the way, in this example, listen to me. Can S0 communicate with S2? Can S0 communicate with S2? It cannot communicate with S2. Are you following me? In a single hop. It cannot communicate with S2 in a single hop. Clear? Why? Because this one can only transmit at what? Lambda 0 and receive at what? Lambda 3. None of them is what? Is the same as the one that this one is transmitting at lambda 2. Clear? Clear? Okay. Let's take another example. Did you understand the difference between a physical? This will be in the final. Did you understand the difference between a physical topology and a virtual topology? Virtual or what? Or logical. Logical topology. Let's take another example so that you understand what I'm talking about before we get to the assignment of this. Another example. Let's assume we have what? We have 5 nodes, each equipped with a single transmitter and a single receiver. A single transmitter and a single receiver connected in a unidirectional ring. When I say connected in a unidirectional ring, what am I talking about? That's the what? That's the physical topology. That's the physical topology. Now, assume that each fiber can support 2 wavelengths. Notice, by the way, before I even continue with this, when we talk about a light path, could we have multiple light paths sharing the same what? Fiber. Can we have multiple light paths sharing the same fiber? Yes, we can, as long as they are of different what? Wavelengths. We cannot have what? Wavelengths, same wavelengths, sharing the same what? Sharing the same light path. Otherwise, there will be what? There will be collision. Could the same wavelength be used? Could the same wavelength be used in different light paths? In different light paths? Yes, they can. As long as they don't have any what? All the nodes are what? Disjoint. Disjoint, which means what? It means, in other words, for example, let me just show you this. I want you to look at this. This light path. This light path. Do you see this light path? Could it be the same wavelength as this light path? Do you see this light path? This light path. Could it be the same as this light path? Yes, it could. Why? Because they don't have any what? Any node in common. They are totally what? Disjoint. Did you get my point or not? Yeah, but this light path, I want you to see this light path. Could this light path and this light path, could they be of the same wavelength? No, they cannot be of the same wavelength because they are sharing the what? They are sharing this link. Did you get this or not? Sharing the same link, you cannot have the same what? Same wavelength. Okay, so let's see what we have here. What we have here, the physical topology, is the following. Okay, this is 0, 1, 2, 3, and 4. And they are connected by a what? It's a unidirectional ring. A unidirectional ring. One more time. Is this a physical or is this a virtual? That's a physical. Are you following me or not? That is the physical. Now, let's start assigning the wave. Now, let's assume the core requests are for the following. 0 to 2, 1 to 3. First of all, do you understand the notation? What does the notation mean? Means I need to establish a communication path between node 2 and, between node 0 and node what? 2. This is the transmitter, this one is the what? Is the receiver. Clear? Okay. Node 0 to 2, 1 to 3, 2 to 4, 3 to 0, and 4 to 1. Can we do it? Let's see if we can do it. Okay. Now, let's see if you can help me. Between 0 and 2, I'm assigning what? Lambda 0. Did you get this or not? Okay, what does it mean? When I'm assigning lambda 0, what does it mean? Remember, by the way, every fiber can support how many wavelengths? Every fiber can support 2 wavelengths. Lambda 0 and what? Lambda 1. Clear? Every node can transmit only at what? 1 wavelength, and it can receive at what? 1 wavelength. So it's not tunable. The transmitter receiver is not tunable. Okay, so I have lambda 0. Answer me the following question. How many light hops are there between 0 and 2? Is it a single hop? So when I don't get responses, I feel a little bit discouraged here. You are not following me. How many physical hops between 0 and 2? 2. How many light hops between 0 and 2? 1 light hop. We call it what? 1 light hop. This one, there is no what? When we say a light path, it means it's an all optical path. There is no optical electronic optical conversion. There is no optical electronic optical conversion. This one is just behaving as a what? As a router, a repeater if you would like. Did you get this or not? Repeating at that wavelength. Did you get my point or not? So we establish at what? We establish a path between this one and this one. Now, between 1 and 3, answer me the question. Can we assign lambda 0? No, we cannot assign lambda 0. Why? Because this is already used. Can I assign lambda 1? So I assign what? I assign lambda 1. This is lambda 1. Continue. Between 2 and 4. So this one is supported. This one is supported. Between 2 and 4, can I assign lambda 0? Between 2 and 4, I can assign lambda 0. Is there a conflict? There is no conflict. So I assign a what? A lambda 0 here. Remember, by the way, every fiber can support how many wavelengths? 2 wavelengths. Every fiber can support 2 wavelengths. That was given in the problem. Clear? Okay. So this one is what? Is already used. This one is already used. Okay. Now, between 3 and 0, can I assign lambda 0? No, I cannot assign lambda 0. Can I assign lambda 1? I can assign lambda 1. So what do I have? This is what? Lambda 1. Did you get my point or not? Yes or no? Now listen to me. So this one is supported, this one is supported, this one is supported, this one is supported. Between 4 and 1, can I support it? I'm stuck. Are you following or not? Even though, listen to me, even though, is lambda 0 available here? Here. Is lambda 0 available here? It is available here. Is lambda 1 available here? It is available here. But that results in what? Discontinuity in the wavelength. I don't have a what? A light path in here. Did you get my point or not? I don't have a light path in here. So this one cannot be what? Cannot be supported even if lambda 0 is available over link connecting nodes. Which nodes? 4 and 0. And what? Lambda 1 is available in the link connecting what? Node 0 and what? 1. Did you get this or not? But I'm not going to have a what? A continuous light path. I'm not going to have a continuous light path. Clear? Clear? What is the virtual topology? Can you show me the virtual topology? What is the virtual topology? Still waiting. How does the virtual topology look like? This is, again, the physical topology. The virtual topology looks like this. Did you get it? Did you get it? That's the virtual topology. This is how, in other words, this network, even though it looks to the eye, as a what? As a ring network. But in reality, it's like this. The 0 can send to what? To 2. The 1, help me. The 1 can send to who? To 3. The 2 can send to what? 4. And the 3 can send to what? 0. That's a virtual topology. Huh? Did I mess up? Did I mess up? No. Clear? Clear? Did you understand the difference between the physical topology and the virtual topology? Yeah. And then Angelos also, of course, will give you some more examples tomorrow or next week or whatever. Did you get this or not? Did you get this idea or not? A virtual topology tells you what? It's a set of what? Light paths. The virtual topology only deals with what? With light paths. As long as there is a light path between any two sets of nodes, this light path is regarded as what? As a single hop, even though in reality it could be what? Multiple hops. One more time. Between 0 and 2, how many hops? Physical hops. Physical hops. How many hops between 0 and 2? 2 hops. In reality, in a virtual connection or in a virtual network, how many hops are there? Just 1 hop, because it's just the same light path. Clear? Oh. So then, let's get back to our chart here. Then the question then become what? How do we assign these what? How do we assign the routes? How do we assign the what? How do we assign the wavelength? In other words, the question becomes a what? The question becomes a routing and wavelength assignment. Now, we saw last time, this is where we run out of time, we have what is known as a static versus dynamic traffic demand. In a static traffic demand, you already know the connection request. In other words, in the example that I just showed you, all of these requests are known ahead of time. Will that make it simpler or harder to assign routes and wavelengths? It makes it much simpler to assign what? Routes and wavelengths, because you already have all of these connections requests in front of you. So in the static demand, the connection requests are known a priori. A priori means what? Ahead of time. The traffic demand is specified by this combination, a source and destination pair. You assign the routes and the wavelengths to satisfy all the demands with minimum number of what? Wavelengths. The way you assign the routes and the wavelengths, you try to minimize the number of what? You try to minimize the number of wavelengths, but at the same time supporting what? Supporting all the requests, if you can. Clear? All the requests you can. Notice, by the way, in here, going back to here, to this example. This example? Which one? Yeah, this example. Between 4 and 1, this request, 4 and 1, we say this request was what? Was blocked. Why do we call it a blocked? Even though this fiber and this fiber can support what? More wavelength. Remember, every fiber in this example can support how many wavelengths? 2 wavelengths. Was there a wavelength available here? It was available here, which means what? The resources was available, but you got what? You got stuck in here because you don't have what? Continuity in the wavelength. We say that this call was what? Blocked. This call was blocked. Clear? Oh. So assign the routes and the wavelength to satisfy all the demands with minimum number of wavelengths, or if the question tells you how many wavelengths do you have, you try to maximize the number of what? The number of demands satisfied for a given number of what? Wavelengths. Clear? So if the question gives you the what, if the question gives you how many wavelengths are available, you try to maximize the number of what? The number of requests that can be what? Satisfied with a given number of what? Wavelengths. If the question gives you the what? If the question gives you the request request demands, then you try to satisfy them all using what? Minimum number of what? Wavelengths. So for example, let's see if you can help me. We did this example last time and then we ran out of time. Let's see if you can help me. This one here is static. We call it what? RWA. What does RWA stands for? Routing and wavelength assignment. These are two separate issues. The routing means what? Establish what is the route, and the wavelength assignment is assign the what? The wavelength. So let's assume that we do have this request ahead of time. 0 to 1, 2 to 3, 1 to 3, 0 to 2. 0 to 1, 2 to 3, 1 to 3, 0 to 2. Now, the request here, the procedure here in the static RWA tells you what? Since you know that, start with the connections in non-increasing order of the number of what? Hops. Non-increasing means what? You start from what? When I say non-increasing in order of the number of hops, what does it mean? To go from 1 to 3, how many hops? How many physical hops? It's 2 hops. Assign those first. So the 1 to 3, let's say we assign them what? Lambda what? Lambda sub 0. Are you following me? Between 1 and 3. Lambda sub 0. Then what? The next one is what? Between 0 and what? 2. Because how many hops in here? 2 hops. So I assign what? Between lambda 0 and 2. By the way, if I assign lambda 0 here, can I assign lambda 0 here also? No, I cannot. Why? Because they will share this. So will I assign what? Lambda 1. This is lambda 1. So this one is satisfied. Are you following me or not? Okay. Between 0 and 1. After I finish from what? The request that goes through what? In here, every request, this request and this request is going through how many hops? 2 hops. Whereas these, how many hops? 1 hop. Start with the one that requires what? More hops. Did you get this or not? Okay. So then what? Between 2 and 3. Where is 2 and 3? Here. What did we say? Assign here lambda 0. Can I assign lambda 1 here? Here. Can I assign lambda 1 here? I can assign lambda 1 here. So this one is supported. Okay. And finally, between 0 and 1, can I assign lambda 0 here? I can assign lambda 0 here. Are all what? Are all the calls satisfied? Are all the calls are all what satisfied? Why? Why? Because I already what? I already know the request. I already know the request. That's what is known as what? The static routing and wavelength allocation. The dynamic. In a dynamic routing, in dynamic demand, connection requests arrive or depart from the network at what? At random. Are you following me? You don't know exactly how many requests are going to come. The light path, once established, remain there for a what? A finite time. What is the finite time? The duration of what? The duration of the call. As long as the call will take, it's a finite time. It's not an infinite time. May require rearrangement of existing light paths to support what? Future demand. This is the same concept that we studied earlier when we were referring to what is known as what? Strictly non-blocking and what? Rearrangeably non-blocking. Strictly non-blocking means what? Means every call can be what? Satisfied without rearranging existing calls. Rearrangeably non-blocking means what? Means all the requests can be supported, but only provided we what? We rearrange existing calls. Rearrange existing calls means what? Change the route. Yes? To support what? To support other calls. Clear? This one is the same idea. May require rearrangement of existing light paths to support the future demands. The routes and the wavelengths are assigned for request in the order they what? They arrive. Let's see if we have a problem here. Which call arrived first? 0, 1. And we are talking about this one. Yes? The dynamic route. What did he assign? You assigned lambda 0 to support 0 to 1. Which calls came first? Second. 2 to 3. He assigned what? Lambda 0. By the way, could he reuse the wavelength? He could reuse the wavelength. Remember, in wavelength routed networks, wavelengths can be reused as long as what? As long as the paths are what? Disjoint. As long as the paths are disjoint. If it is joint, you cannot do it. Okay, which call comes next? 1 to 3. He cannot assign lambda 0 to 1 to 3. Why? Because lambda 0 is already used here. Can he use lambda 1? So he uses lambda 1 to establish. By the way, how many hops? How many light hops between 1 and 3? Oh, there is only one light hop. How many physical hops there are? 2 physical hops. This one and this one. Now came 0 to 2. Can you support it? Between 0 and 2. Between 0 and 2. Can you support it? By a what? A light path. By a light path. Can you support it? Notice, by the way, in here you could use lambda 1, but in here you cannot use lambda 1. So that's a what? Discontinuity in the light path. Similarly, in here you could use what? Lambda 0. But in here you cannot use lambda 0 because it's what? Because it's already used. So in here between 0 and 2, can this call be supported? This 0 and 2, can it be supported? No, it cannot be supported. Are you following me or not? It cannot be supported. But if I rearrange the wavelengths, while the calls are what? Taking place, can I support all of them? I can support all of them, and we already saw it in here. Did you understand that or not? I can support all of them, but in here, the dynamic routing and wavelength allocation, the assignments and the routes are assigned on a what? As the request comes. As the request comes, you assign the what? The wavelength. Clear? Okay, good. Now, let's look at how we are going to select routes and wavelengths, different procedures or different algorithms. First of all, the route. This is the route and this is the wavelength allocation or the selection. Routes. We have different types of what? Algorithms. Different types of algorithms. First one is what? Fixed route. Fixed route. In other words, once you decide on a route, it's fixed always. In other words, between a node and another node, you fix a certain route. So fixed route, only one route, usually the what? The shortest one, is provided for a given node pair. Are you following what? So which means what? Between one node and another node, you will say what? The route is always what? It's always the same. Clear? It's always the same. Upon arrival of the request, that route is examined for free what? Wavelengths. If none, the request is what? Rejected. Did you understand this algorithm? Did you understand this algorithm? You have a fixed route. When a call comes between those two nodes, you judge, remember, this is the route selection. This one is the what? Is the wavelength selection. In the route selection, when a call comes between two nodes, then you examine the what? Is there a wavelength between what? Between these two nodes along that fixed route. If there is, the call will be what? Supported. If none, it will be what? Rejected. Okay. Another algorithm tells you what? Alternate routing. Alternate routing, more than one route is provided. More than one route is provided. They are still fixed, but you will have what? More routes. So between any two pair of nodes, you will have what? You will have route number 1, route number 2, route number 3. When the requests come, you check you check to see if route number 1 is there a wavelength available. If not, what do? You check what? Route number 2. If not, you check what? Route number 3. This is what is known as what? Alternate routing. More than one route is provided, ordered and searched in a non-decreasing order of the number of what? Hops. What does it mean when I say non-decreasing order in the number of what? Hops. Non-decreasing means what? Means you start by looking at what? You start by looking at the shorter route and then what? Go to the what? To the longer one, to the longer one, to the longer one, and so on and so forth. And the third one is called what? Exhaust routing. Exhaust routing means what? All possible routes are what? Are searched. Exhaust routing means what? All possible routes are searched. Clear? Okay. Now, let's look at the wavelength. I will give you examples on each one of them in just a second. Let's look at the wavelength selection methods, which we can classify into several types. The first one is called what? MU. MU stands for what? Most used. Wavelengths are searched in non-increasing order of their what? Utilization. What does this mean? wavelengths are searched in non-increasing order of their utilization. What does it mean? You start looking at what? At the wavelengths which are mostly what? Used, and then go to the what? To the wavelengths which are less used. Did you get this or not? This is yes or no? This is called the MU. Next one is called the least use. And the other way around. Wavelengths are searched in non-decreasing order of their what? Utilization. Starting from what? Starting from the one that is least used, going to the what? To the wavelength that is mostly used. Clear? Mostly utilized. Okay. Fixed order. Fixed order means what? Wavelengths are searched in what? In some fixed order. You decide on an order and you search the wavelengths based on that order. Random order, Rn. This fixed order, this random order, Rn. The wavelengths are searched in a what? In a random order. Clear? In a random order until you find a wavelength that is available. RWA algorithm may select routes and wavelengths one after the other, or they may be selected what? Jointly. Selected jointly means what? You select a route and a wavelength at the same time. One after the other means what? You select the route first and then you select the what? The wavelength. It can be done either way. Let's see if you, did you understand it? Did you get it? Let's see if you can help me with examples. You will see something like this in the final exam. A wavelength division multiplexing network has 4 wavelengths, lambda 0, lambda 1, lambda 2, and lambda 3. At some instant of time, they are used on 2, 5, 1, and 4 links. At some instant of time, they are used on 2. What does it mean on 2? Means lambda 0 is used over how many links? 2 links. Did you get this or not? Yes? Okay. Lambda 1 is used over what? 5 links. Lambda 2 is used over what? 1 link. And lambda 3 is used over what? 4 links. Let me ask you a question. Which lambda is the most utilized? As lambda 3. Is it lambda 3? I'm sorry. Lambda 1. I'm sorry. Lambda 1. I thought this one. Lambda 1 is the one that is most utilized. Which one is the least utilized? The least utilized is what? Is lambda 2. Clear? Okay. A new connection request arrive for the pair between what? S and D. A new connection request arrive for a pair of S and D. Assume the route is chosen. Assume the route is chosen. Assume on this route, lambda 0, lambda 2, and lambda 3 are free. And lambda 1 is what? Is not free. Lambda 1 is not free. Did you get this or not? Yes or no? Okay. What is the MU? What will, in which order you will search? If you are using MU, which one would you search? You will search, first of all, what? Lambda 1. Yes? You will search then what? Lambda 3. Huh? I messed up? I messed up? Lambda 1 is 5. Lambda 3 is what? 4. Lambda 0 is what? 2. And lambda 2 is what? 1. So you search in this order to see which one is what? Which one is available. Are you following me? Now, why did I select lambda 3? Because lambda 1 is not available. The question tells you lambda 1 is not available. So the one that you choose is what? Is lambda 3. Clear? Okay. What is the LU? What do you search? In which order? You search in the order of what? Lambda 2, lambda 0, lambda 3, lambda 1. You start with lambda 2. Why? Because the lambda 2 is the one that is least used. You start with lambda 2. And then what? Lambda 0, lambda 3, lambda 1. Which one you select? You select lambda 2. Clear? This one is the least used and it is available. So you use. Fixed order. Search in the order of what? Lambda 0, lambda 1, lambda 2, lambda 3. Fixed order. Which one do you select? Lambda 0. Random order. Let's assume this is your order. Random order. Which one you select? You will select lambda 2. Why? Because lambda 1 is what? It's already used. Clear? Clear? Okay. Now, let's take the routing stuff. Fixed routing. Let's assume that we do have the following network. Let's understand it carefully. We have a fixed routing algorithm. We have the network with how many nodes? 5 nodes and 6 links. These are the 6 links. Each link can support what? 4 wavelengths. Each one of these links can support 4 wavelengths. The wavelengths are what? Lambda 0, lambda 1, lambda 2, and what? Lambda 3. Clear? Okay. Remember one more time. If lambda 0, if any given lambda is used over a link, it cannot be what? Reused for another connection. It cannot be reused for another connection. Clear? Okay. Wavelengths are lambda 0, lambda 1, lambda 2, and lambda 3. And you request 4 connection between 0 and what? 4. The wavelengths are available on each link as follows. On each link. On lambda 0 is used over which link? L0, L2, and L3. Did you get this or not? Lambda 0 is available in, the wavelengths available on each link is as follows. Lambda 0 is available here, is available here, and is available here. Lambda 1 is available where? Here, here, and here. Lambda 2 is only available at what? Here. Lambda 3 is only available at what? L0 and L3. Clear? Okay. Now, let the fixed route between what? Between 0 and what? Between 0 and 4, this is the fixed route. Fixed route means what? You fix it ahead of time. What does it mean? It means any request from 0 to 4 will go through this. How many wavelengths are available on here? On L0, how many wavelengths are available? On L0, available is what? Is lambda 0 and what? Lambda 1. And lambda 3. I did not say this. Lambda 0, lambda 1, and lambda 3 on L0. L3, on L3, lambda 0, lambda 2, lambda what? 3. So how many wavelengths are available in both? How many common? It's lambda 0 and what? Lambda 3. I'm not sure, did you understand? Did you get this or not? Only lambda 0 and lambda 3 are available on these these links that are what? Common. Now, if you are using the most used wavelength, which one would you choose? Would you choose lambda 0 or would you choose lambda 3? If your criteria is the what? Is the most used. Which one would you choose? Lambda 3. Why? Lambda 3, the choice is between what? Lambda 0 and lambda 3. Lambda 3 is available over how many links? 2 links. Whereas lambda 0 is available over how many links? 3 links. So the one that is most used is what? Is lambda 3. Yes? This lambda 3. What is least used? You choose what? Lambda 0. If you use fixed choice, you use what? Lambda 0. And if you use random, you choose one of them at random. Either you choose lambda 0 or you choose lambda 3. Clear? Clear? Yes? Okay, good. Now, let's see. Alternate. Fixed alternate routing. Fixed alternate routing. Same scenario, same example, but now assume 2 candidate routes. 2 candidate routes between 0 and 4. The first one is what? L0, L3. The second one, the second route is what? L1, L5, L3. So there are 2 candidates. One of them is this. How many hops? 2. How many physical hops? Physical hops. 2 hops. And the other one is what? 3 hops. Yes? I will start searching for what? I will start searching to see if I can assign wavelength on the what? On the route which has the what? Least number of hops. So I have 2 alternate routes. Which one am I checking first? I'm checking the first, the route between what? The R0, I call it R0, which is what? Which is this link and this link. And then I will check R1. The wavelength available on each link is as follows. Again, this is the availability on each link. So when he says lambda 0 is available at L0, L1, L2, means what? It's available here, It's available here, and it's available here. Did you get this or not? Yes? Okay. And same thing with the other landers. Clear? Okay. The availability of wavelengths on different links is as follows. L0 is available, lambda 0 is available at what? At L0. At L1, what do I have at L1? Lambda 0 is available. Lambda 1 is what? Available. Lambda 2 is available. Lambda 3 is also what? Available. Clear? This, by the way, this is the same as this, but in here I'm talking about what? The lengths. The lengths. Clear? On L2, which one is available? Lambda 0, lambda 1, lambda 2, and lambda 3. Again, all of them are available. On L3, lambda 1, lambda 2, and lambda 3, and so on. Clear? Okay, how would you assign? How would you assign? Can you use this? R0, L0, can you use this route? Between L0, in other words, this and this. What do you see? You see L0 and you see L3. Do they have a wavelength in common? No, which means what? This route failed. Did you get this or not? If you do have a single route, what would happen to this request? What will happen to this request? If you are checking only what? One route. What will happen to this request? This request will be blocked. Did you get this or not? But luckily right now we have a what? We have another route. R1. I can use what? R1. What is R1? R1 is L1, L5, L3. What do they have in common? This is the L1. This is the L5. And this is the L3. Can you tell me, do they have something in common? Which one is in common? It's lambda 3 is common and lambda 2 is common. So I can use either lambda 2 or what? Lambda 3. Which one? Which one I use? Depends on what? The wavelength assignment algorithm that you are using. If you are using the most used, which one would you choose? Would you choose lambda 3 or would you choose lambda 2? You would choose lambda 3. Why? Why would you choose lambda 3? Because lambda 3 is available over how many links? 1, 2, 3, 4. Yes? Whereas the lambda 2 is available at what? 1, 2, 3, 4, 5. Which one is more used? Lambda 3. You choose lambda 3. Whereas if it is least used, you choose what? Lambda 2. Did you get it? This will be in the final exam. Did you get it? Did you answer what I mean by LU and MU? No, you didn't. Jeez. Do you understand why R0 cannot be used? Can R1 be used? How many wavelengths are available? What are they? Lambda 2 and what? Lambda 3. Which one do I choose? Depends on the algorithm that I'm using for what? For the wavelength assignment. Let's start with lambda 2. How many lambda 2 is available in how many links? Is available in what? 1, 2, 3, 4, 5. So lambda 2 is available over how many links? 5 links. Lambda 3 is available. Available means what? Not used. Lambda 3 is available on how many links? 1, 2, 3, 4. Which one is more used? Lambda 3 or lambda 2? Lambda 3 is more available. Sorry, it's more used. It's available over how many links? 4 links. Whereas the other one is available over how many links? 5 links. Which one is more used? Is lambda 3 is more used. Did you get this or not? And so I choose lambda 3. If I'm using least used, I will use what? Lambda 2. If I'm using a fixed assignment, a fixed order, I will choose what? Lambda 2. Because the order that I'm searching is what? Lambda 0, lambda 1, lambda 2, lambda 3, lambda whatever. 4. Is there a lambda 4? There is no lambda 4, just lambda 3. Clear? Anyway, if you still have problems with this, see me in the office. Exhaust routing. What does exhaust routing mean? You start searching the what? The routes one by one, until you get what? Until you get one that works. Let's see. How many routes are there between 0 and 4? Can you tell me by looking at this, how many routes between 0 and 4? This is one of them. 1, 2. Is there another one? Which one? 3. Did I exhaust all the routes? I exhaust all the routes. There is what? 1. By the way, can I go this way? No, I cannot go this way. This in this direction. Did you get this or not? So in here I have what? This. I have what? This. And I have what? This. Exhaust routing algorithm does not predetermine the route. It keeps the network state information in the form of a what? A graph. You look at it, a graph. The state information is dynamic, changes with the traffic. The best route is chosen according to a certain criteria. For example, if you are using Dijkstra algorithm, you try to find the what? The least cost path first. Results in better performance, lower probability of blocking, but slower. Why is it lower probability of blocking? Because you are going to go through what? You are going to exhaust all possible what? All possible routes. But it's slower because you are going to go and do the search. Did you get this or not? Okay. More suitable for centralized control, if you do have central control. Let's see if you can help me here. The wavelengths available on each link is as follows. Lambda 0 is available here and here. Lambda 1 is available here, 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 and here, and so on and so forth. How many routes can be? Look at this. Don't look at this. You are looking at this. How many, first of all, can I use this route? Which is the shortest one. By the way, if you apply Dijkstra algorithm, here, assuming that every hop is 1 unit long, same length, then the Dijkstra algorithm will give you what? Will give you this as the shortest path. Can I use this? At L0, how many wavelengths are available? L0. L0, only one wavelength is available. L3, where is L3? Only one wavelength is available, which is not the same wavelength. Yes? So I cannot use that route. What is the next route? This one. Okay. 1 second. By the way, we missed one route. We missed one route here. One more time. This is one route. Yes? This is another one. The third one is this. We missed this one. What's the matter with you? How come nobody said anything? Did you get this or not? Which happens to be, by the way, the longest what? The longest route in terms of the number of what? In terms of the number of hops. But in this example, there is only one route which has a free wavelength, which is the what? L1, L5, L2, and L4. Which wavelength is available over each link? It's lambda 1. Route chosen by the FR and the FAR have no free what? No free no free lambda. The only free lambda we have is the lambda 1. What is this FR stands for? Okay. Fixed routing. What is FIR stands for? Fixed alternate routing. Clear? Clear? Okay. Now, least, this another one. Least congested path routing. Least congested path routing. What does that mean? It tells you what? Choose the route that is least congested. What does it mean? Choose the route where there are large number of wavelengths available. Do you follow me on that? If I tell you, for example, in here, I want you to tell me here, in this example, just in this example, just an example. Okay, which link is the least congested? which of these links are least congested and which one is mostly congested. First of all, which one is the mostly congested? It's what? L0. Why is it L0? On L0, only what? One wavelength is available. What does it mean? It means the 3 other wavelengths are what? Are used. Did you get this or not? Yeah. Which one is the least congested? L4? Where did you get L4 from? L4, what is available on L4? Oh, sorry, lambda 0, lambda 1, and lambda 3. Did you get my point or not? Yes? Okay, so let's look at what this least congested path routing. The least congested path routing, this abbreviation of this, chooses the route with the least congestion among available routes. The greater the number of free wavelengths, the less congested the route is. Can be used with alternate routing. Candidates' routes are chosen offline, and the least congested is what is chosen. Do you understand what offline means? Offline means what? Means in a centralized control, by looking at them, you see which one is the what? Which one is the least congested, and then you can what? You can assign those wavelengths. If there is a tie, choose the one with the minimum number of what? Hops. If there is a tie between paths in terms of their congestion condition, choose the one that has the minimum number of hops. Let's see if you can help me. Again, same thing. The wavelengths available at each link is as follows. How many routes do we have alternate? We have 2 candidates between what? L0 and L3. And the other candidate is what? L1, L5, and L3. On R0, how many wavelengths are available? On this path. On this path, how many wavelengths are available? On lambda 0, how many wavelengths are available? 2 wavelengths. And on lambda 3, how many wavelengths are available? 3 available. Yes? Combinations of 2, how many available? On R0, only 1 wavelength is what? What is this lambda 1? Ah, lambda 1 here. I keep forgetting. L0 has what? Lambda 1 available in it. Yes? And L3, where is L3? L3 here. How many wavelengths are available? Lambda 1 and lambda 2 and lambda 3. So on R0, only 1 wavelength is what? Is available. Whereas on R1, this route, 2 wavelengths are available. 2 wavelengths are available. What are these 2 wavelengths? On the R1, on this path, L1, L5, and L3. How many are available? Lambda 2 and lambda 3 are available. Which one would I choose? I will choose R1 because it's the what? It's the least congested path. I would use the least congested path. Clear? Clear? Okay, good. Okay, there are, by the way, many other algorithms for what? For routing and wavelength allocation. Question? You have a question on this? Cannot hear you. Soft? Oh, the question is solved. Oh, okay, fine. The question is solved. Okay. Now, let's look at the relationship between the routing and wavelength allocation and what? What does WC stand for? Wavelength conversion. Now remember, whenever we have wavelength conversion, what does it mean? It means that we are going to be using a what? An optical, electronic, and what? Optical conversion at every router. Are you following me or not? When we talk about a light path, there is no what? There is no conversion to electrical. Everything will be what? Optical. But when we talk about wavelength conversion, which means what? It means a node is going to receive at a certain wavelength. Yes? The modulation, the information is modulated onto that wavelength, but that wavelength is not available over the next hop. So what does it need? It needs a wavelength conversion. In a wavelength conversion, you will demodulate first. First of all, you will change optical to what? Electrical. You will demodulate the information in the electrical domain, and then you what? Modulate another wavelength, modulate the same information on another wavelength that is available on the what? On the other side. Okay, WC, eliminate the wavelength continuity constraint. WC, which is what? Wavelength conversion. Eliminate the wavelength continuity constraint. Wavelength continuity constraint is a requirement for a light path. When we talk about a light path, the wavelength has to be what? Continuous. To eliminate this constraint, we use what? Wavelength conversion. Of the wavelength assignment subproblems of the what? Of the RWA. Increases wavelength channel reuse, reduce the number of what? Required wavelengths. Reduces the probability of what? Connection blocking. With wavelength conversion, you can reduce all of these things. However, it will add to the what? Complexity of your network configuration, and it will also add to the what? To the delay, the latency. This is not a transparent, this is not a transparent operation. It's a non-transparent. Non-transparent means what? You are going to feel the delay because your wavelength is going to be what? Your signal is going to be converted from optical, electronic, and so on. So, let's see if you can help me here. Let's assume that we do have the following situation. I have lambda 1 here. This one, lambda 2, is available here. Lambda 3 is available here. Lambda 4 is available here. Are you following me or not? This is wavelength. This is without wavelength conversion. Without wavelength conversion, how many wavelengths do I have? I have four wavelengths. But with wavelength conversion, I can use what? Only 3 wavelengths. What is it? This one to this one is what? Is lambda 1. This one to this one, I can go with what? Lambda 2, and then I can switch to what? Lambda 3. You follow me or not? Between this one and this one, I can use what? Lambda 3. And between this one and this one, I can use what? Lambda 2. See, lambda 2 cannot go what? Between this one and this one. Why? Because there is already lambda 2 in here. Are you following me or not? But if I use conversion in here, I can go from what? Lambda 2, I can switch to what? To lambda 3. Lambda 3 is used between what and what? In this example, lambda 3 is used between this one and this one. Clear? Yes or no? You didn't get it. What do I have? Because between this node and this node, I want between this one and this one, between this one and this one, and between what? This one and this one. There are 2 calls between this one and this one. Did you get this or not? Okay, so without wavelength conversion, how many wavelengths do I need? I need 4 wavelengths. Lambda 1, lambda 2, lambda 3, lambda 4. I can use this, 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 and this. In here, I can use what? A wavelength conversion here. I can support all of these calls with how many? With only 3 wavelengths instead of 4. What are they? Between this one and this one, the first call. Remember, between this one and this one, there are what? 2 calls. 2 calls. In here, what was it they supported? By lambda 1 and what? Lambda 4. In here, this is lambda 1. In here, I can use what? I can, to support this one to this one, I can use what? Lambda 2, and then I switch to what? Lambda 3. Did you get this or not? Convert to lambda 3. Between this one and this one, I use what? Lambda 3. Between this one and this one, I can use what? Lambda 2. Clear? And this is the benefit of the wavelength conversion. Wavelength conversion, it will result in what? Reduction in the number of what? In the number of wavelengths. Clear? This will also be in the final exam. I will tell you where should you put the wavelength converter such that you reduce the amount of what? Reduce the amount of wavelengths and reduce also the probability of what? A blocking. Reduce the probability of blocking. Clear? Oh, now let's look at the remaining part of this set. Let's look at the existing architecture with the wavelength division multiplexing. The existing SONET, we already talked about the SONET. This is prior to wavelength division multiplexing. SONET, which is the synchronous optical network, and SDH, which is the synchronous digital hierarchy. Remember, this is the European or the Asian standard. This one is the US standard. High-speed network. What do you see? You see a whole bunch of routers running over what? Running over a SONET network. We call it what? IP over what? IP over what? SONET. Sometimes they call it what? PoS. PoS stands for what? Packet over what? SONET. So we do have the routers here. Everyone is communicating at a certain. These are what? The STS. STS stands for what? The synchronous transport signal. When it says 12, what does it mean? The rate STS 12. 12 times what? 51.84 megabits per second, resulting in what? 622.08 megabits per second. 622.08 megabits per second. Now, why is this one a bottleneck? It says a bottleneck. Why is this a bottleneck? We are talking about what? 622 megabits per second. Is this large or small? Well, this is relatively small. Remember, inside the core, you are going to support the traffic from what? All users rather than from a what? From a single user. If we were talking about a single user, 622 megabits per second is a huge. But if we talk about what aggregate, it's what? It's behaving as a bottleneck. Again, as I told you, this, when I showed you before, when we talk about this on it, most of them are based on what? A ring. Do you see this? This is a ring. Ring topologies. Ring topology. Most access rings are OC3 and OC12. Most backbone rings, which are the high-speed rings, is OC what? OC48. What is the OC48? Anybody? OC48 is what? It's 48 times what? 51.84, which is roughly what? 2.5 gigabits per second. 2.5 gigabits per second. Transport of route rates higher than OC48 using existing will require significant and costly changes, which means what? If your rate is more than OC48, if the aggregate rates, transporting of rates, more than OC48 using the existing architecture require what? Significant and costly changes, because you need to add what? You need to add more fiber and you need to add more what? SONET equipments around the edges. Clear? Clearly, upgrading the SONET and the SDH network every time broadband data interfaces are upgraded based on increased IP traffic is not an appropriate solution. Every time the traffic increases, you need to what? Upgrade your network. That's not an appropriate solution. Clear? You would like to have what? A better support on the core. This one, if you see this one, this is the IP SONET WDM architecture. By the way, currently they are thinking even of removing SONET, which means what? IP runs directly over what? Over WDM. But in this case, you have to remember the router needs to have interfaces that supports the what? Supports the higher rate of the what? Of the wavelength division multiplexing. This one can support much higher rate than this one. Why? Because these on a single fiber, you can support what? Multiple wavelengths. And every wavelength can support what? Large number of what? Large number of channels, like I will show you shortly. Clear? So in here, you do have these what? These, the IP routers, all of these are the IP routers. Remember, in here, what will take place? All the intelligence, the processing, for example, the call admission, the call monitoring, and so on and so forth. The thing that we studied earlier in the semester, which is what? The quality of service provision. Clear? Quality of service provision. The call admission, call monitoring, and so on and so forth, all of these things. This is regarded as a what? As a transport mechanism, just a transport mechanism. These are the bunch of what? SONET equipments. The SONET equipments, the added drop mux and the line termination. The line termination, these are the SONET part. And in here are connected by what? By a wavelength division multiplexing. This network is a what? Is a wavelength. In other words, the SONET is residing on top of what? This is a wavelength division multiplexing. Here we do have what? Multiple wavelengths interconnecting these. Clear? So this is the architecture of what? IP over SONET over the wavelength division multiplexing. Now, the evolution of the wavelength division multiplexing is similar to that of the SONET, the architecture. For example, we do have a point-to-point This is a point-to-point. We have multiple wavelengths multiplexed on a single fiber, and here demultiplexed into these. This is called what? A point-to-point. Then they added the what? The wavelength division multiplexing. The added drop. We have what? Point to multi-point. So for example, in here we do have what? Multiple wavelengths. In here we add a what? An ADM. ADM stands for what? Add, drop, mux. Lambda 1 will be dropped. Lambda 1 will be dropped. Lambda 1 will be added from different source. You follow me or not? Okay, then what? What is this? Lambda K is dropped, lambda K is added, and so on and so on. You put the wavelength division multiplexing along the way. You could also have the cross connect, where you do have what? Multiple wavelengths coming in here, and the cross connect will switch them. This one will be switched to here, or to here, or to here, and so on and so on. We call it what? Optical cross connect. OXC, optical cross connect. This is the what? This is the IP over what? Over the optical transport network, which means what? What did I remove? What did I remove from the previous one? See this one? What is it? IP over what? SONET over what? Wavelength division multiplexing. This one is what? Is IP over what? Over an optical transport network, which is what? Which is all wavelength division multiplexing. That's the IP, and I'm going to connect the IP directly to the optical cross connect. All of these are what? Are wavelength division multiplexing. Wavelength division multiplexing. I remove this on it. But in this case, to be able to do that, I need to make sure that this port or this interface of the router can handle what? Can handle higher rate than what? Than just a basic what? Basic SONET. Clear? In the SONET, we are talking about what? In megabits per second. In here, we are talking about what? Gigabits per second. Routers needs to be able to what? To support this. By the way, in all of these, you see in all of these routers, you have what is known as an element management system. An element management system. Element management system means what? Means the module that will control this system only. And then we do have the what? The NMS, which control the entire what? Entire network. This is the NMS, the network management systems. Clear? Okay. This is the IP over what? Over OTN. Alternative architectures, again, IP over the WDM, IP over OTN, IP routers interconnected over a reconfigurable optical transport network consisting of multiple what? Cross-connect systems via what? Via DWDM. In here, the optical cross-connect are connected via DWDM, whereas in here, the IP routers are connected directly over what? Over DWDM. In here, the DWDM is not connecting the what? The routers. It's connecting the optical cross-connect. In here, the DWDM are connecting the IPs. Let's look at it this way here so that you understand what I'm talking about. Look at this one and look at this one. This one is the architecture that we talk. What is POP stands for? POP, the point of what? Presence, where the traffic is going to be collected. These are a bunch of routers. What is this? What is this one? This is a wavelength division multiplexing. This is what? WDM, 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 WDM. Are you following me or not? This is called what? Routers connected via what? The DWDM links. In here, the routers are connected via what? An optical cross connect, and these are connected via what? The wavelength division multiplexing, not the routers. Did you get this or not? The routers in here are attached to what? To these. And these can be configured. In other words, you can switch it here, you can switch it here, and so on and so forth. Question? Oh, for 5 minutes. I couldn't hear you. Clear the difference between these and two? Yes? This one actually is what? It's faster, but this one require what? Higher rate for the what? Higher rate for the routers, for the routing interfaces. This one requires what? Less, because the cross connects are connected via the wavelength. Okay. This is the pros and cons, which we discussed. If you are running IP over DWDM directly, the pros and the cons. IP routers with OC48, OC192C interfaces and aggregate throughput reaching 100s of what? Gigabits per second. 192 is what? 192 is roughly what? 10 gigabits per second. Transport functions like switching, configuration, and restoration are all moved to the what? To the IP layer. In here, all of these in here, in this, the switching functionalities are done by what? By the optical cross-connect. Whereas in here, all the switching functionalities is removed to the what? To the router, to the IP layer. So transport functions like switching, configuration, and restoration are moved to the IP layer and accomplished by several protocols that can provide a unifying framework. IP routers control the end-to-end path selection via traffic engineering, and all the intelligence are done in the what? In the routers. Supports peer-to-peer models and so on. So the con is what? Can router technology scale to port counts consistent with the what? Multi-terabit capacities without compromising performances? Are you following that? If you increase the what? If you increase the rate of what? Of all of these interfaces to reach the terabits that can be supported by fiber, will it result in what? Will result in degradation in the performance or the reliability and so on and so on. Again, a big question mark. Okay. This is the what? This is the IP over OTN, the pros and cons. One more time. Optical transport network consists of what? A bunch of what? Optical cross-connect switches, and the routers are connected to them. And these are connected via the what? The wavelength division multiplexing. In IP over DWDM directly, the routers are attached to the what? To the DWDM directly. Did you get this or not? Okay, so this one goes through the what? Goes through the pros and the cons of IP over OTN. Reconfigurable optical backbone provides for flexible transport infrastructure. Why? Because every reconfiguration and the switching is done by who? By the optical cross-connect rather than by who? By the router. So it's what? It's more flexible. The core optical cross-connect network can be shared with other services such as ATM, frame relay, and SONET, and so on. So allows interconnection of IP routers in an arbitrary logical mesh topology. When we do the what? The cons, it means once you add those optical cross-connect, then you need to add a what? You need to add the management that will add, or you are adding a certain layer. You are adding an extra layer between what? Between the IP and the DWDM. I want you to think about this as what? The second layer, which means what? You need to do a lot of what? Traffic engineering. You need to do a lot of management to handle what? To handle the optical cross-connect part of the network. Optical network, which provide provisions, a physical light path between the edge routers, could lead to inefficiency in the routing, in traffic routing from a global perspective. So every technology has a what? Has its pros and cons. Okay, last arch before we continue next time, which shows you what? How the optical deployment is, how the optical fiber is deployed over the access, the metro, and the backbone. Let's see if you can see this is a company, some company, another company, and a different company. Some of them are wireless. Some of them are what? Some of them are wired. These are what? These are the access. This is the what? The metro. And these are the what? The backbones. You notice, by the way, the backbones are either rings or what? Mesh type topologies. Mesh type topology. Everything goes into what? Into a hierarchical fashion. Now, when we say fiber, this one is also fiber. Fiber to the what? Fiber to the building. We'll see that next time. Fiber to the building or fiber to the home. What are these, by the way? These are what? Cellular or mobile devices connected by a what? A SONET ring. And the SONET ring is connected to the what? To the regional or to the metro network via what? Via fiber. All of these are fiber. Clear? Clear? Okay. Next time we will continue on what? On other deployments of fiber in the last mile, in the access network. Clear? Okay, good.
The time is 4 o'clock. The time is 5 o'clock.